your experience and the perspective, and hopefully get some feedback from the university.
Yeah, so when the time comes, I can link you with the right colleagues. As I said, like this is in another school, so I don't have too much involvement, but I know that these programs exist. So of course, I can always link you guys like with the right people in the
Thank you,
School of
really
Engineering.
appreciate that. Thank you very much.
Yeah, no problem.
Thank you, Dr. Israr. So we can start with the webinar. So hello, everyone. So first, I would like to thank everyone for joining us today. In today's session, we have one of the prestigious speaker, Dr. Rodrigo with us. So thank you so much for being with us on the behalf of IEEE Dhofar University Student Branch, College of Engineering and Department of Electrical and Computer Engineering. We are really thankful to you for your time. So before I give the floor to Dr. Rodrigo, I want to have a brief biography or brief introduction about Dr. Rodrigo. I want to introduce to you. Dr. Rodrigo is basically a senior lecturer and associate dean of research in School of Computer, Data, and Mathematical Sciences at Western Sydney University, Australia. He has been conducting the research in cloud computing since 2008 and contributed to diverse aspects in the field, including multi-cloud, energy-efficient cloud computing, and edge computing. He is one of the original designer and developer of CloudSim, a simulator for cloud environment. And this simulator is very popular among the researchers, and it has been used by many researchers around the world. He has more than 70 papers, which has nearly 18,000 Google Scholar citations. His research interests include Internet of Things, Internet computing, blockchain, and their applications. He has also been awarded with IEEE TCSC Award 2017. He is Fellow of Higher Education Academy of UK, Senior Member of IEEE, and Senior Member of ACM. So today he is going to speak about fog and edge computing and its challenges and emerging trends. Dr. Maruf, can you hear me? So over to you, sir.
So it's time 12:30, so I think we should start.
Oh,
So
okay.
on the behalf of CRC.
I made sure to open this presentation with a photo of our campus. So this is the campus where I'm located in the university. So other things to introduce myself also. I have been working with cloud computing like since before cloud computing was a thing. Like so, I say like very early, like in that time. And I was able to see all this transition of what existed before clouds, then what happened and what's happening now. And I hope that I can give you this perspective of what's changing and in this area of clouds, that's this part of fog or edge computing. Okay. Especially in the beginning, like I know it's early in the morning, like for you. So to make sure that you are all awake, I may ask like some questions in the beginning, and after that we progress in a more traditional way. Okay, so here is what I'll be talking today. I want to talk about like clouds, fog, edge, and all these things that relate to things in the sky. Okay, then I will go specifically about the challenges, and then these emerging trends. And if there are some of you that might want to research in the area or know what's coming next, like that's what I expect to achieve in this part 3. And then of course I will be closing. Okay. Feel free to write questions in the chat. So if I see them here, like I could try to answer as I go, like otherwise I will be answering at the end of this presentation. Okay, so let's start. Okay, and as I said, like just to make sure that everybody's awake, I show here a slide with many things, okay? And I will ask you to tell me, okay, like what all these things have in common. Okay, so we have a number of things here. I tried to bring things that could kind of relate to different of your interests. So if you like soccer, or if you like video games or movies or technology or astronomy, like, so can you tell me something about this figure? Anyone wants to give it a go on what all these things have in common? Anyone? Okay, so what they actually have in common is that all these things that are here happened in 2006. Okay, so in 2006, Google acquired YouTube and Twitter was founded, and you had that World Cup where you have that situation like in that match of France, like I think it was semi-final. Nintendo Wii was released, and the first of these James Bond movies with the current actor that you have the last one coming now. So all these things happened in 2006. Okay, why 2006? So what could have happened in 2006 that's relevant to this talk? So, okay, this one might be a bit harder. So that's what happens in 2006. The first products of AWS were released. Okay, so here we have S3, or the main ones that became the kind of the foundations of cloud computing. So in March 2006, S3 was launched. And here we can see that August 2006, a beta of EC2 was launched. So we had this first notion of object storage to be consumed as a service, and the first notion of being to pay for servers per hour to use, like to run your workloads. And then, so for those that are not familiar with this, so object storage, it's a type of service where you upload the files and you can keep only for yourself, for your own applications, or also make it available for the public. But before that, most times the way that you'd get files being shared in this way would involve you hiring some server in this type of co-hosting facilities, or in a data center, or in your own company data center, installing some type of web server to serve this content and let people log into it. Okay, with S3, you don't need to install, run a server, you install application servers on that, upload your files, and make sure that these computers don't break. Okay, so here you just upload your files. They are automatically replicated across the data center, so you avoid the risk of losing this data, or so it's very high available, very highly durable. Okay, and you only pay for the volume of data that's stored there, and also some data transfer costs for that, but no need to operate servers to get there. And Amazon EC2, then you get a virtual machine, so you choose your operating system, you choose how is the machine you have, like how much memory, how much CPU, and at that time you'd pay per hour. So you'd pay something like in excess of 8 cents of dollar per hour of the use of the server. Okay, like these days for Linux servers, we get charged per minute to do that. So things like in a way like became cheaper than that. Okay, but here is the information. So 2006, okay, these building blocks of cloud computing were launched. Okay, and then lots of things happened since then. So Netflix started streaming in 2007. So that's also was like a big change. So before that, if you wanted to watch movies, you would rent a movie in your local store, or you'd buy them, or you would wait like to watch it on TV, or you'd have some cable service for that. Okay, so here you started having the chance of watching what you want at the time that you want. 2007, we also had the first iPhone, and that was also a big change in behavior. Like before that, you'd expect that people would most times be using the internet from like sitting in a desktop, okay, or not with mobility. So even when you had desktops, we would not usually like be using like too much on the go, okay? So we tended to have our mobile data, the location of your server is much more static than what iPhone enabled people to get, okay? But look at the time, the internet was still not that good, okay? So you'd still like have problems with the quality of like what you could stream and time for buffering and what type of things you could do with your iPhone. But then in early 2010s, the 4G became quite widespread. And at that point, you get enough quality of service there to be able to watch movies with a reasonable resolution in your phone, in the train on your way to your work or to the uni. Okay, so lots of change of behaviors here. So if in the olden times you would be sitting using a kind of a wired broadband connection to be able to watch movies, now you could get the same thing done in the screen of your mobile phone in your way to school. Okay. And then since the mid 2010s up to now, all of these Internet of Things expansion came. Okay, so it started like we had one device here, one device there, and then we saw an explosion in the consumption of data by these devices. Okay, so it's a huge amount of gigabytes of data that are being like moving around all the time. Okay, and of course, coming soon, we have 5G. So in some countries, like here in Australia, rollouts already started. It's not available everywhere, but we are talking here about mobile services that are competitive with the best or the fastest types of wired broadband that you can get. Okay, once 5G is completely like rolled out, you can expect that people can retire their fiber-based backbones and everything. Okay, so that's a big change. Okay, so making this long story short here. Okay, so in these 15 years, the way that web applications are designed and used change a lot. Okay, so think of that. Like, so before that, users would be static using things in their laptops. Okay, now the users are on the move, usually with smaller screens. So the way that you present that content also needs to be dynamic. And in fact, there is so much variety now of devices that you also needed to change the way that you design your applications to be able to match whatever screen is available for the users. Okay, multimedia content is much larger now than it used to be 15 years ago. Okay, and before that, it was not kind of a streaming consumption. So what you have is that you would download the whole thing first and watch later. You just didn't have usually enough bandwidth to be able to watch on the go. Okay, and now streaming is kind of a default. I understand that this talk is being streamed today. Okay, probably this will not be possible in 2006. Okay, when cloud started. Social networks also evolved over time, and now we have this like TikTok and other social networks that are completely based on videos. So early versions of Facebook were also mostly static content. You'd get some text and some photos, and these days we have these social networks that are completely based on video and nothing else. Okay, so again, the load that type of application now use much bigger than what we had before. Okay, IoT is practical and widely adopted. So personal, like this type of Alexa devices, light bulbs that you can use the internet to control, air conditioners, heaters, fridges, like you name it. Okay, like things are there, and like most of our electronics these days can connect to the internet, and usually they are, and you get data going to one side to the other. Okay, and the result of all of this is that too much data is being generated and transferred. Okay, and with 5G, we can expect even more of that. Okay, so the consequence of that is that that model of centralized cloud data centers is becoming obsolete and expensive to run. Okay, so think about that. When web servers were, web applications were more static, people were like not moving, and everything else, we had a type of need. And for that type of need, centralized cloud data centers, very powerful with thousands of machines, were able to do a very good job. Okay? But these days, the data being generated, so being uploaded and downloaded, are everywhere, and too much of it, and sometimes in small batches. So another challenge of IoT is that we go away from that model of needing lots of bandwidth, and now you need lower latency, because we are working sometimes with very quantum data there. Like you have some sensors measuring the temperature here. You know, you are just uploading a few data points, like bytes of data, but with high frequency. Some of these protocols, internet protocols, were not designed for this type of interaction. Okay, so they are mostly used like where the time to establish the connections are compensated by the amount of data that are going back and forth. And many of these IoT data sometimes goes to one direction, so usually from the sensors to the cloud, okay, and in very small quantums. So the architecture that was developed since 2006 was not designed with these use cases in mind. Okay, and then we started seeing research there where people saw that latency is becoming the main concern of enabling these applications to work well. And to solve this problem, then we got edge, fog, like sometimes people call mobile computing. I talk about all these different terminologies. Okay? So what is it? Okay, so it's a decentralized compute and storage, okay, usually in a location that's closer to end users than the data centers. So this figure here like tries to represent it. You are generating data in your, so in your house, so IoT, and then it needs to be uploaded. So if you are your provider of these IoT services using clouds, it will need to send this data from your house to the nearest cloud data center that it's like thousands of kilometers away, potentially in another country. Okay. So now with edge computing, we try to bring this computation capacity closer to where the users are. Okay, so we don't take all the way to the cloud. We might establish a smaller scale, what they call edge location, okay, where we have some amount of computing capability and storage capability to serve this local region. So now my data doesn't need to go all the way up to the cloud, it will stop midway. Okay, where this happens, that's where sometimes there are these differences in the interpretation of what is the meaning of edge, fog, and mobile computing. So some people talk about using own servers. So some agriculture applications and industrial IoT applications, you have some extra computing capability, a bit more powerful than you get like closer to the devices to do this local processing. Okay, and you might offload part of it to the cloud. Some other scenarios don't say that users needed to operate their own edge devices. We have this notion of cloudlets that would be a smaller scale data centers, or even kind of a one server attached close to the radio base stations of mobile networks, for example, or closer to the points usually where your mobile networks connect to the main internet backbone. So that's a good point where you could keep a number of servers to help with this communication. Okay. Other researchers advocate to try to use networking equipment. So maybe you could use routers and switches to also do some small scaling processing in addition to the routing that they are doing. Okay, as these equipments become more powerful, also they might be able to assume this type of responsibilities. Okay, and as this sometimes researchers call the approach edge or fog or mobile based on this where. Okay, but this is not kind of widely accepted. We have to look at the literature. We see people referring, using the same term to refer to different things all the time. Okay, but what really matters here is this where. Okay, because as I said, like some people say that if the where is the networking device, then you have fog computing. Other people, otherwise it's edge. So it's a bit confusing on that. Okay. And to show that, I show here a bit like different definitions. So we have this definition here from 2017. That's one of the earliest ones. So this author, I think it's the first one to propose these concepts that became what's today's edge computing. Okay, so the term is used in earlier publications before 2017, but there is a paper in 2017 that provides this clear definition of that. Okay, so substantial computing and storage resources are placed in the internet's edge, so close proximity to mobile devices. Okay. We have this other definition here, that's where data processing occurs in part of the network edge rather than completely in the cloud. We have this other definition here where it prefers calling. So you see this definition here is very similar to the definition above, but it calls fog what the other author is calling edge. So that's all these terminologies arise at the same time, and there was no complete agreement in the literature. So what we do is that usually every time that I want to use these terms in my publications, I need to provide the reference. Okay, so I need to say whose definition I'm using in my paper. Otherwise, it's very hard for people to understand where my processing is happening. Okay. Fog computing in particular was a term introduced by Cisco. Okay, and they use it in a bit of different way. So that's it's more about, as I say, like they define how the edge should work. So they accept that there is this infrastructure, that's the edge computing, and the fog computing is more how edge should work to accomplish certain types of tasks. Okay, and I saw other definitions also. I saw stuff like called dual computing as well. Like, so it's the terminology is, I'd say, like it's always evolving. So it's important to always acknowledge the one that's in use. What really matters here? Okay, so what's the important takeaway from here? Okay, here are the points. So data is being generated from sensors, so say like IoT sensors or other data sources. Okay, and this data can go to the cloud that usually is far away but has huge computing capacity, or goes to a nearby device where it's closer, so lower latency, gets there faster, but that device doesn't have the same power to process that in the cloud. Okay, so usually these near devices might have some do some aggregation in the data. So again, to minimize that quantum data transmission to the cloud, we could have these intermediate devices aggregating the data before uploading to the cloud, or sometimes aggregating and computing locally. Okay, or sometimes offloading without aggregating. So, or sometimes it might what to do like partial offload. So it could assume the responsibility of certain types of processing that can be done in that device, while the heavier one would be sent to the cloud. A very practical scenario. So there are some devices here that can do image recognition. So usually these sensors or these smart cameras, they upload the training. So they might collect data and send to the cloud for training, and then they download the model. So the inference happens in the camera, while the training happens in the cloud. And sometimes when the camera cannot recognize the object, it might offload that particular inference to the cloud to somehow like see if the extra computing capacity can help to identify what the object is. Okay. So again, the heavy parts of it, that's the training, and the difficult inference goes to the cloud, and the simpler the inference that work like with the models that exist can be done in the device itself. Okay. Another thing to consider is pricing in the edge layer. So there is different assumptions being made in the literature. Some people assume that edge devices usually are cheaper than the cloud device to operate. Some people say the opposite. So maybe it's a matter also of what is exactly your edge. Okay, so what type of device might define the cost, but still what happens is that when you are trying to model it or making decisions about what runs where, you might also need to take into consideration that costs differences between running the edge and running the cloud. Okay. Another challenge of the edge is that it's likely to be heterogeneous and smaller. So although you can assume that a large scale data center, you have enough computing capacity of the same type of hardware, it's harder to make this assumption in the edge because you have much less devices and less control. Okay. And clouds also, because they use virtual machines, sometimes they help to abstract and containerize the capacity of this hardware. So even if you get a very powerful server there, you still don't get the full server for your use. You get a small capacity, you get 2 CPUs and 16 gigabytes of RAM of that big server. Okay. And you also could get another 2 gigabytes of RAM and another 2 CPUs from a smaller scale server, but you might not notice like too much difference in the processing of them because of like collocation things as well. So you don't need to know what's the hardware. Okay. And with edge computing, you tend to be exposed to the hardware, especially because there is also a bigger variation in the type of processors that you are using in the edge than in the cloud. It's still like most of the cloud data centers, probably still Intel dominating. And in IoT, we have lots of RISC processors like in use. So like the 2 types there. So we expect also this difference in the computing architecture to be more visible and probably affecting more your decisions at the edge layer than at the cloud layer. Okay. So what are the challenges of that? So what's the problem of that? So why I'm talking about this and why this matters? So I try to say, okay. So first, okay, it's hard to use the edge. As I said, like there is no kind of a clear things to facilitate the use. So these existing programming frameworks are things that are there that were supposed to help you to use these heterogeneous multi-layer facilities are not intuitive to use. And I would say, like in the experience that I had in my own research groups, that sometimes it's better not using them and developing all the things by ourselves than trying to use them. It's just because depending on the time that you have to the project, the learning curve for these frameworks are so big that it's better like just not using it and develop it by yourself. So that's a big problem for adoption. Okay, so we need more viable frameworks or ways that people can abstract all this complexity and use it. Otherwise, it's too hard for normal companies to adopt this model. Okay. There is another issue with proprietary devices. So some of these devices are pretty hard to integrate because the protocols are closed. And the only way that you get to be able to interact with some of these IoT devices by using their own apps that they provide you. And because of sometimes licensing issues, you are not allowed to kind of reverse engineer the protocol to try to replace their app by your own kind of edge solution. So it can make a bit hard to use these devices. So you might be constrained to the type of device that you can use to communicate with the IoT devices because of the type of the proprietary protocols that are in use and what are the type of software that they provide to you to use them. Okay, offloading is pretty hard to execute. So say unless it's a kind of a really type of separated task, as I mentioned, training and inference for machine learning, for example. Okay, so that's easier to do because these are 2 steps that are completely decoupled one from another. So it's easy to say inference is in the edge and training is in the cloud. But when your processes are not quite clear where they separate, that's a bit hard to achieve. So imagine that if you have an application, you are doing a video and you want to do some processing of the video, so generating special effects, like in your videos on the go. Okay, so you might have some of it happening in your mobile phone. So I don't know, like you add in the image a person that's not there, or you try to remove something from the scene that's there and you don't want it to appear. Okay, so maybe your mobile phone would be able to handle part of this, but at some moment the battery might start like giving away. Look, you will not have enough battery to complete the recording while you have to remove someone from the scene as you do it. But this act of trying to separate, okay, like let's delegate this task of removing the person of the scene to the cloud, that's not there. Okay, it's pretty hard to achieve practically, like with applications. Okay, and also like these conditions for offloading. So again, like, so when so if in the previous example of doing this effects, like in the videos, if you know a specific task that you want to offload, it could be done before. So you could develop your app with the capabilities of offloading that particular task. But in the other hand, when you have like too many tasks and you might not know beforehand what you'd like to send to the cloud and what tasks would you like to happen in your phone or in your IoT device, that's much harder to achieve. Okay, and as I said, like in many cases, the cost of implementing like these solutions for offloading might outweigh the benefits. Okay, so you might just, like I don't need to do it in real time. I can just do it in the traditional way of edition of the video after I record it, for example. So you could go around alternative solutions if the cost of this more technological solution is not worth it. Okay, and no one talks about the deployment. So the other issue is where this runs exactly. So some people talk about containers, like Docker containers, and they are a good solution, but they don't run anywhere also. So, and it might be challenging to explore heterogeneity when you have this type of solutions. Okay, so nothing of this is happening at the moment, and that's why. So if you'd like to ask me later why we don't see a broader adoption of edge computing to solve day-to-day problems, the issues are here in this slide. Okay, so that's not a mature technology at the product side of it to be used. That said, I said like there are some companies that develop very good applications for some specific domains. Okay, so for example, edge computing for agriculture. So there are companies that can get to a farm there, add the sensors to the fields, install these edge servers somewhere like in a silo or in a safe place that can do some pre-processing and some analysis, and that can send the rest of the data to the cloud for visualization and reporting, for example. Okay, but to buy the whole solution. Okay, it only does that in the end. The same for industrial Internet of Things, some smart home automation process, but they are all kind of, they are not general solutions or something that help to build any application and run in the edge in the same way that you can do in the cloud today. So they are really, if you have a very specific problem that fits the model of that company, you might go there and buy the product. And then they come and they make it work. Okay, but it's hard, like not possible to port it to another domain for that because the application was not developed for that. Okay, so what a general kind of a programming language or framework or kind of a toolkit that you write your code here and it compiles code that can run in the edge, in the cloud, and the device, like these things are not there yet. Okay, and while they are not there, adoption is going to be limited. Okay, some of these other challenges, so heterogeneity in the edge layer. I said like, so on itself, like it's a bigger problem that what I was able to mention so far. deployment issues, I'll talk more next. Programming models for the edge, handling failures. That's also like a big problem. So something goes wrong in this complex application that you have. So getting back to that, you have part of your application in your phone or in your farm, part of the application in the edge, part of the application in the cloud. Some of these parts doesn't work. It's hard to say like if the problem is in the servers, if the problem is in the application itself, or even pinpoint exactly where it broke. Okay, so there are lots of opportunities for research there. And the problem of security and trust in the edge layer. So this is also research on itself. Okay, how do you trust, given that the edge are heterogeneous, you might not know exactly who runs that, how can I somehow make sure that there will be no leakage of data that I put on the edge, and that some encryption techniques might be needed. Okay, for today's talk, I want to talk in these two things. So in the next section of this talk, I will be focusing solutions for these two challenges here of deployment and programming models for the edge. Okay, so program deployment. Okay, one of the things that's emerging now, it's this notion of serverless computing. Again, the concept itself has been there since 2014. Okay, and as I write here, it's a kind of one of the most misleading terms in our area. Okay, so serverless computing doesn't mean that you get some computing happening like magically. Okay? It just means that people that run the code don't need to operate the facilities to run it. So if you go back to that notion of cloud, okay, so in the cloud, I rent a server, okay, per hour, like say a virtual machine. I deploy the software that I need in that virtual machine and run my application there. I have this notion that there are virtual machines there and I pay for them per hour. In the serverless model, I upload my code, my application code to a service and it runs. Okay, and I pay for the total time that it runs. I'm not sure on how many machines were deployed to run my application. Okay, I know that there is some guarantees that if there are more users coming, more infrastructure will be available for my machines. So the response time for the users is more or less consistent. Okay, so I don't need to handle this type of scaling. I don't need to handle failures of servers, okay? And I don't pay per hour. And why this can be an advantage? Because in the case of IoT, for example, you have one sensor generating one data point per hour, and it needs to upload to a server. Your server runs 24 hours a day to operate effectively during like 24 small time windows during the day. Okay, so I pay for a whole day of use, and I'm using, I don't know, like even let's say like 1 minute per hour to do whatever it needs. So 24 minutes, and I paid 1 day for that. Okay, with serverless, I receive 24 requests, I process them, it takes me 24 minutes. I pay for this 24 minutes of processing that happened. And I don't know exactly how many servers and what are the characteristics of the servers that supported my application. Okay, so as the team that develops and runs that software, I don't need to have concerns about hardware platform scalability. Okay, however, the way that it works is a bit strict at the moment. So your application needs to be stateless. So you cannot keep state of application within this server, like you need to keep it elsewhere. The computation is better off asynchronous, and it has short timeouts. So you can expect that at the maximum 15 minutes, if your computation cannot complete in 15 minutes, it's not suitable to run on this model. Okay, and there are some open source options available for that. So OpenWhisk from Apache and OpenStack has this Jinling solution that offers these serverless capabilities for people to deploy in-house. Okay, so what are the issues here that research teams are looking at? Okay, first is what it takes for developers to adopt. Okay, so our applications may require large refactoring to fit this required model. So if my application has states, I need to find a way of getting out of the application. If it runs for a long time, I have to somehow decompose it. Okay, and maybe to become a workflow, and that's another topic that has been also explored a lot in the scientific literature in a couple of years. Okay, my application might not fit the model at all, and then maybe it's not even a refactory. I might need to rethink the way that I build this application to fit on that model. Okay. For operations perspectives, okay, so it makes it a bit harder, but I see lots of research these days about serverless at the edge. Okay, but it's pretty complex, and we have this issue of data placement, of like where we build the data that's serving like the serverless applications. Okay. But that said, there are a couple of opportunities there to explore in this front. So how to support this statefulness in the applications. There are lots of very good works like in this area where people are coming like with all the types of solutions. Okay. Automation of workflow descriptions as a way to help people to decompose these complex applications that take a long time. Service discovery is always a problem. So when you have all this, say, serverless on the edge, how to get to know where they are, because they are serverless. So they are not there until they are actually accessed. Okay, so how you get to know that when you want to access a certain service, where it is and how you can find and access. So that's a big issue as well. A coordination when you have many of these serverless edge functions trying to collaborate in like to solve the same goal, it brings some coordination issues. Handling of heterogeneity, handling of volatility, it's another issue. So these applications are short-lived, and across the execution of these serverless functions, you might be actually being exposed to different hardwares every time, because this is serverless, like you don't have a guarantee of what's the particular piece of hardware that is running your functions. Okay, and best approach is to hold application data. So when you want to use the serverless model, okay, and again, like this serverless capabilities will appear in different places. So where you put the data and how you protect it and how you minimize latency for that. So these are all ongoing research areas. There are some very interesting literature in all these topics. And as this evolves, you can expect to see more of these serverless concepts being available. Okay, and supporting this type of edge computing applications. The second topic that I want to talk is about hybrid computing models. Okay, so what's that? So for many years, we had this scientific workflow application models that were popular to build scientific applications. Okay, that's a bit on how they look like. So pretty much you break your application in a number of stages. Okay, these stages have dependencies. So we model this as graphs. Okay, so the edges of these are the applications themselves, and then these arcs like tell the dependencies. So it means that in our case here, that orange application can only start after we finish that green one. Okay, and you see like some aggregations there. For example, our gray application there in the middle can only start after all the black ones completed their processing. So we create this kind of a bottlenecks that need to aggregate lots of data and then splits and parts that can run in parallel. That's a very popular model for development of scientific applications. This example that I'm putting here is real, is an application for building mosaics of images of the sky. So pretty much you have lots of telescopes capturing data from the sky, and this workflow builds mosaics of that data. Okay, so there are many of these workflows supporting many types of data analytics also. Okay. So, and you can see it as a type of a batch job. Okay, so it means that there is no expectation many times that this workflow will be able to complete kind of in real time or quickly. So usually you'd go there, you schedule, so you put like this request to the facility, look, I want this mosaic here to be built. And like a couple of hours later, or a few minutes later, if you're lucky, or maybe days later and weeks later, if you are unlucky, you receive a message there, look, your job completed. Here you can download the output from this address here. Okay, so this was seen as a batch model. So we don't, the objective here is getting as many as these workflows completed on time and not too much reducing the execution time of one of them. Okay. But recently we saw the emergence of another pattern that's more suitable for these modern times of real-time data analytics and Twitter. That's the streaming model. Okay. It has many similarities to workflows, okay, but the computations are much more short-lived, okay, and as I said here, it occurs in always-on resource. What it means? So it means that that's the type of platforms to support real-time data analytics. So your sensor generates some data, you need this data to quickly go to some processing to generate some output for someone. Okay, so here in these workflows, these typical scientific workflows, you have lots of data. So it's large amounts of data that are the input, and the output can be equally large. Here we are working with very small data, so sometimes like a few bytes at once, but maybe many of them come at the same time. Like think about Twitter. Okay, that's exactly what's happening there. Tweets on themselves are quite small, but you have many of them coming. And as they come, they need to go through specific stages of processing until it becomes some output that's consumed in another part of the system. So Twitter is one example from the time that someone sends the tweet from their phone until it's kind of visible in the application like backend and back like to the users that follow and all of them. It goes to many stages. And many analytics also real-time working with this scheme. So as I said, like you receive data from some sensors, it goes to different stages of processing, aggregations, maybe calculation of averages, or anything else until it's incorporated some meaningful output. Click analytics is another one. So many sites these days are instrumented to kind of to get to know what you are doing and where do you click and how long do you stay in a certain website. So every time, many websites are kind of collecting this data all the time of your behavior while you are navigating the website. And this data is collected and sent to a backend to go to some real-time analytics like this. Okay, so that's all the types of applications that benefit of this model. So here, as I said, like they are kind of always on. You don't know exactly when your next stream data will arrive. You don't know when the next tweet will come. We don't know when the next reading of the sensor will come. We might not know when's the next time that the user clicks in some part of your website. Okay, so you keep this infrastructure running all the time, ready to consume this input, and you might need to scale each of one of these edges there like as needed, because some of them might be more take longer to process than others. You might need to scale them independently. Okay, so here the objective is low latency. So you want each of our operators, each one of these edges of this graph to complete as fast as they can. Okay, so look, scientific workflows have been there since the 80s. Okay, streaming is more recent. It really kind of took off after like Twitter and this type of, and they published their environment. That's so the framework like to process that, and then people started doing lots of research about that. Okay, so the next challenge now is combining these two things together. Okay, so not much to the practical thing. So there are frameworks there that can achieve that. The question here is modeling this problem. So workflows, again, like have been there for 40 years, they are well understood. Streams have been there also like for like at least 10 years. The actual research of these models like are older than that. Okay, so it's good to see more research in how to model, like to capture the nuances of this attempt of merging low latency, high kind of income rates of things with this more computation heavy batch processing to achieve a common goal there. Okay. So it's important to understand more applications that follow this model. So what are the concrete cases that you have for this, and what are the real requirements of this type of applications? And then you need to find ways of fine tune, like the throughput of these different sequences of batch processing, streaming process. We saw, I see like people talk about aggregation windows. So you don't try to keep doing the streaming as a streaming. We might aggregate the streaming and then throw it back to the system as a kind of a micro batch, like the sense of course, you don't store it for hours to build a huge volume of data. We just do enough to kind of cause some activation or some behavior that better resembles batch processing. Okay. This kind of interrelation where bigger streaming flow increase the time of batch processing, so you need to be able to handle that. Okay, so this interplay between these two models make that improvements in one may delay the other and vice versa. So ways to solve this problem are needed. Okay, this is already hard to achieve in a data center level, and when you bring to the edge dimension, so it becomes even higher. Okay, so here's some other interesting research questions. So 5G, so how 5G will change all of these? Okay, and for people of networking, they're like overlay networks over these like 5G connected devices, because today we still need all the communication going to the base stations. With 5G, we'll be able to have devices communicating peer-to-peer. So it will change the way that you can get data flowing, like in this ecosystem of cloud and edge and IoT. Okay, we talk also about collaborative or cooperative edge computing, where you get these nodes cooperating to perform tasks. Okay, and they can also cooperate for storage purposes. And then you have the issue of protecting data consistency and trust of the data that's there, and the security of that as well. And I see also this definition of IoT, edge, and cloud continuum, where you would like to see applications being able to move across the layers as they go. Okay, so your application should be independent of what exactly is happening. So if it happens that at the moment, for some reason, it needs to run in the cloud, it's fine. If in a few minutes or hours later, it might be better to bring that application back from the cloud to the edge, for example, to the IoT layer, it should be able to happen. Okay, so this is a bit of more cutting edge research. It's talking about this IoT edge cloud continuum, but it's the possibilities here are big. But again, it's still today like hard to get the basics right, but that's where the most kind of recent research is going towards. Okay, so it's this type of models and architectures, and so not only infrastructure, but also the models that are required to support the seamless movement of applications across this continuum. Okay, so takeaways of today is that changes the way that applications and content is consumed occurred in the last 50 years, okay? And it reduced the efficiency of centralized data centers. Edge computing helps with that by bringing computing close to where the data is generated. And serverless computing and hybrid computing models are promising computing models for the edge. Okay, so just before I finalize, I would like to acknowledge my colleagues that work on that. So some of the ideas that I discuss here come from discussions with my colleagues, Associate Professor Bahman Javadi and Kenan Matawi from Western Sydney University. And some of these works were done by our PhD students, Raed and Mohammed. Okay, so that's what I had for today. Thanks for listening, and I'm happy to answer questions.
Thank you so much, Doctor. So if anyone has any question, either he can put in the chat box or he can open his mic and to ask the question.
Yes, I stop sharing now.
Okay, sir.
Yeah. So any questions?
Yeah.
Or any
Just thank you so much for your nice presentation and talk. So just I have one question that you talked about serverless services. So if I think of 5G, so do you mean D2D communication, device to device communication?
Yeah, that's one way to go. Yes, so that's something that 5G will enable, and it will change a lot also the way that we model our applications. Yeah, so this aspect of device to device communication 5G probably is one of the biggest game changers for the research that we do now to what's needed, because it helps a lot to reduce latency. Okay, so before that, application like all the data goes to the radio base and back. And now I get, so especially across the layer, so you can imagine that if you have this layer of edge devices, that although they are connected today via 4G network, they are close to each other, but with high latency communication. And with 5G, they will be able to communicate with each other. So it will reduce a lot the latency and maybe the way that you make decisions about where things run. But this is a bit independent of serverless. Serverless, it's because still, if your devices don't have enough capacity to process, it still needs to be sent elsewhere. Okay? So serverless is more about that when I'm deploying my applications, I don't need to be concerned in understanding what's the infrastructure that's supporting it.
Okay.
Because I don't have to handle.
Second is that you also talked about the hybrid computing. So somehow our cooperative computation. So I think that device to device communication when we have, so this we can also go in that direction. I mean, both the goals which you discussed, we can go through with D2D, device to device communication. At the same time, we can have serverless, and at the same time, we can have hybrid computing.
Yeah. Yes, they are complementary. They don't interfere. So when one can be seen as the way that these devices connect to each other, and the other is about the protocol. So I would say this part of D2D and 5G, they are more like in these lower layers of the architecture, the hardware and the networking, and the collaborative or cooperative is application layer. So it means that they are trying to achieve a common goal. Yeah. Okay, so it's different from
exactly. And one more thing that, for example, you said that nothing is concrete about the edge, that what it will be. Yes. So, I mean, it can be any kind of device. For example, if we think of the vehicular network, aerial vehicular network, so maybe drones can also work as edge.
Yeah. That's a good comment. That's also very emerging areas that have lots of attention, that it's exactly, they call this vehicular edge computing. It's quite common now, like research topic. It's good because in this case, we could have, especially when autonomous vehicles come, like what do you have now? Maybe you have this fleet of cars working together to understand the environment. So instead of everybody doing the same computation to understand the same environment, each one does a part, they share the data, you reduce the energy consumption and gets more information about the environment faster. So that's also a very interesting research area.
Okay,
so that's a good one.
How do you think about the tethered balloon? So which the concept is emerging these days. Can it work as an edge computing devices?
Sorry, which?
Tethered
balloons?
Yeah.
Yes, they could. Depending on how high they are, maybe like, maybe the latency is still good. No, think like wherever you can have servers, like where you can put computing capacity. Maybe the issue with these balloons would be energy.
basically they'll be connected by the fiber at the down. So also I think maybe they are getting charged up.
Yes, and it's the same for mobile. So today, the main limitation of getting the mobile to the work is not that our mobiles are not powerful enough. It's just that usually you don't have energy to do that. I said, like if you put your mobile to do some heavy computation, you run out of battery. So autonomy of this device is one of the main issues that we have to look at.
Exactly. I mean, for example, in the case of UAV and in the case of balloons, we need to also look about the battery, that how much, because they are operate for limited time, for example, especially the UAV. So thank you so much, Professor, for your wonderful talk and answers. So is there any more questions, please? I think Dr. Star is there, so our engineering college dean, so he wants to say some words.
Thank you, Dr. Rodrigo. It was a very fruitful and engaging presentation for our students. I'd like to thank you on behalf of the IEEE student branch at Dhofar University, on behalf of all the faculty and students at College of Engineering, and on behalf of Dhofar University senior management team. I really appreciate that. We're looking forward to fruitful and collaborative research. Hopefully, this will be the first of many talks. And I would like to also invite our esteemed colleagues and faculty members to also present at your prestigious institution. And again, thank you very much. And I would like to just ask just one final question. So you started your presentation with, you know, where we were in 2006 and where we are now. So where do you see us in the next 15 years? Where will this technology take us?
Yeah, good question. I think that the one that I see it's more autonomous, everything more autonomous, I would say, and needing lots of that. So we talk about like vehicles, like we see already like this presentation that people already can coordinate the drones. So I would expect more things happening on the place, maybe less in the cloud, I would say. So especially like when you see like this 5G is like emerging. So I would say that lots of the current infrastructure might be obsolete by them, that things, maybe we will not need all these physical networks that you build, like, you know, and I hope that people understand more. I would expect that development is going to be easier, that you'll be able to say write code for people that are here, software engineers, that you don't need to worry about where it runs. So you write your code and there will be compilers and things there that will make it work anywhere that you need.
Right,
So, that's other things.
I have Dr. Manaf, our assistant dean. He's an expert actually in blockchain, so maybe he has a few questions and some concluding remarks.
Not really an expert, but I'll just like, first of all, thank you, sir, for this clear, informative, and concise presentation. It's really nice. And of course, we hope to have more such informative presentations from such renowned researchers like yourself to benefit our students mainly, and of course, our faculty. I have, it's basically regarding the main thing that comes, of course, to mind now is with the blockchain. So before we were, of course, we were talking about blockchain, and it was like very hot topic. And now something came up, which is, of course, like relies on blockchain, the metaverse. So how can they integrate together? How can they go along together, if we can say this? Or do you think that they both, like the topic you talked about and the blockchain, do you think that they're going in the same pace? Do they, like, there is you know, is there difference in pace between them? Can they catch up other?
Yes, thanks, a good question. I think that because blockchain evolved much faster. I think that there was lots of interest, and because of all these Bitcoins and all of this, like that, there were more resources in the area, and it evolved much faster. You know? There are talks about using that blockchains might be a solution for the problem at trust at the edge layer. Because if these edge layers are heterogeneous and maybe operated by different providers, you might not trust like who else is running the other device, and the blockchain might offer a kind of a layer of data assurance that you know that no one is tampering with the data that's there, you know, like so. But yes, Edge has much catch up to do, because simply I think that because of all these resources available for blockchains, the research kind of took off very fast. While Edge got like stagnated, like it's going more kind of slow and steady, but there is a space for these technologies to come together. So maybe Edge can benefit from blockchains to again, to give some assurance of trust in these like heterogeneous layers. And yeah, so maybe in this part of cloud and edge and IoT continuum, like you could have also a solution for energy. We need also these blockchain protocols like to improve like the way they work now, and maybe the answer for that might somehow be in the way that these edges and clouds and these things work. So that's still like to be done. So I see more research as blockchain supporting edge, then that's it, like to give this assurance to how edge as infrastructures could support the blockchain, but could have like some space there for research in the area.
So you mean like, I mean, either one can benefit the other, can support the other one?
Yes, at the moment, yes. At the moment, I see more blockchain supporting edge, not the other way around.
Supporting edge, okay.
Yeah, so as I said, like many researchers see blockchain as the solution for trust in these edge environments. But how edges can help somehow blockchains to work better, it's like not much there yet.
Okay.
That's a good area to explore. Like.
One more thing, like, I mean, of course, since this is for IEEE for the students, basically, like for some of our students might be interested in this. If you have any suggested introductory material or like, I don't know, lectures or books that they can rely on in order to, you know, familiarize themselves more with this topic, that would be also.
I can think about that. Maybe I can share some literature. I can send it later, the list, because I might need to compile it, like some kind of a basic lecture. Yeah, basic readings about like the area for different levels of interest. Yes, I can compile a list, and since I don't have it right now, but I can share. Like.
Thank you so much. Thank you so much again. Thanks a lot for this presentation. I'll give back the floor to Dr. Najm.
Thank you so much, Dr. Israr and Dr. Manaf. Dr. Imran, Head of Department for Electrical Engineering, also want to say something.
Thank you very much for your nice presentation on the behalf of IEEE student branch at Dhofar University. I would like to thank you again, once again.
Yes, and thanks for inviting me to be here. Like it's my pleasure to be here and get to know you. And yes, let's hope that you can build something like out of this. Yes.
Thank you very much. Thank you again. Have a great day.
Thank you. Yes, have a good day.
Everyone have a good day. So that's the end. So see you in the next some session. Thank you so much, Dr. Rodriguez.